Welcome. We are in day 2 of section 7.3, Isomorphism and Planarity. And this video is a little bit different. I'm basically just going to walk you through the worksheet, and we'll talk about some of the big ideas and what you need to know to complete the worksheet. This completed worksheet is due 2 hours after class. So unlike all of your other notes uploads that were due before class, this is due after class. And I really want you to think about using class time to work with other students and ask any questions that you have, asking them questions or asking me questions. All right, let's take a look at what this worksheet has. Two big ideas in the worksheet. We're going to prove Euler's formula and the fact that K33 is not planar. Recall K33, that was also called the utilities graph, and it looks like this. It's a complete bipartite graph. The idea is that no matter how you move the vertices around, no matter how you bend the edges, so long as you don't disconnect anything, there's no way that you can draw this without edges crossing. This is not a planar graph. Two things, two big ideas, and the first one is Euler's formula. Let's prove that. So Euler's formula says that for any connected planar graph with V vertices, F faces, and E edges, it must be the case that V plus F equals E plus 2. So consider the connected planar graph to the right, this little guy right there. There are 4 ways that we can grow it into a larger connected planar graph. 1, we could add an edge to make a loop. Or 2, we could add an edge connecting 2 distinct vertices. Or 3, place a new vertex on an existing edge, thus splitting the old edge into 2 new edges. Or 4, create a new vertex off the graph and attach it with a new edge to a vertex on the graph. So you can see that each grow option 1 through 4 creates new vertices, edges, or faces. Check when you agree. Now let's move on to the proof of Euler's formula. This is a proof by induction. So the base case says, let's suppose that graph G consists of only a single vertex and no edges. So G is simply a single point, just like that. So how many vertices, how many faces, how many edges does this thing have, and does Euler's formula work? Okay, you answer those. Now for the induction hypothesis. Suppose that graph G is a connected planar graph with V sub G vertices, F sub G faces, and E sub G edges. And we really are assuming that Euler's formula does work for graph G. Then let H be the graph that results from growing G in one of those 4 ways above. For each growth option, I want you to figure out VH, FH, EH, and show that Euler's formula also works for graph H. So the first is given to you. Let me show you how to step through this part number 1. Let's suppose that we add an edge to make a loop. So my graph G, I don't know, it's some abstract graph, but it has a vertex, and I just add an edge to that to make a loop. Notice that V sub H, the number of vertices in H, that hasn't changed. I haven't added any vertices, so that's the same as the original G. The number of faces in H, well, that's 1 more than the number of faces in G, right? Because this face right on the inside of that loop, that was added. And the number of edges in H, that's 1 more than the number of edges in G, because I just added that new edge, that new loop that went around. Okay, so I start with V sub H plus F sub H. Those are the two things that I need to add together in Euler's formula. Well, V sub H, that's just V sub G, and F sub H, that's F sub G plus 1, in this particular case, in this case 1. Now, Vg plus Fg, this is where I use the induction hypothesis. I know that Euler's formula works for graph G, and so that is E sub G plus 2. And that's what gives me E sub G plus 3 at this point. Well, my goal is to prove Euler's formula for H, so I know that the beginning of my formula is VH plus FH, and I know that the end of my formula should be EH plus 2. How is this last step made possible? Maybe I can take my third equation and solve for E sub G. So E sub G is really E sub H minus 1. e sub h minus 1. And so by plugging this in for my e sub g, that's what allows me to get my last expression, e sub h plus 2. All right, so for you, do something similar for parts 2, 3, and 4. See that you can complete the table. Thus, essentially, here we go, I'll scoot that up a little bit. You'll complete the proof. In every case, we see that the number of vertices in H plus the number of faces in H equals the number of edges in H plus 2, and so the proof is complete. So complete that for me. The second big idea is, number 2, proving that K33 is not planar. We need two lemmas. So you see part A is a lemma, and then a little further down part B, that's a lemma, and then we'll get to the actual proof. So let's talk about the lemma at A. A lemma about cycles. The size of a face is the number of edge lengths that an ant would encounter if it walked around the boundary of the face. Write the sizes for the faces that have not been completed. So some of these have. So the 3, and the 5, I'm looking at the graph on the left. Let's look at that 5. Why is that 5? Well, if I imagine the ant, it starts off at some point, and then it walks along one edge. That's 1, 2, 3, 4, 5. It walked along 5 edge lengths, so the size of that face is 5. Let's look at the 8. So an ant starts somewhere on the outside, say close to that 8, and then it walks 1, 2, 3, 4, 5, 6, 7, 8. 8 edge lengths. And so the size of the large unbounded face, that has size 8. Where it gets a little bit confusing, take a look at the far right graph, that number 11. Let's justify why there really are 11 sides. So the ant starts somewhere, let's say right there, right below the 11, and starts walking to the right. So 1, 2, 3, 4, 5, 6, 7, 8. Now here's where you got to be careful. 9, 10, 11. So even though these are single edges, they're counted twice because we count it once for each side of the edge. And so in this case, the total size of the unbounded face is 11. You complete the numbers for all the other faces that aren't numbered here. So it turns out that the sum of the face sizes is 2e, where e is the number of edges in the graph. And in fact, that's actually the lemma that's important here in part A. The sum of the size faces is 2e. This is kind of interesting. Do you see how this relates to something earlier that we studied? The degree sum. The degree sum of a graph equals 2e. So maybe there's some kind of a similarity going on here. The question says, why is this so? And you don't need a lot, maybe just a sentence or two to think about why this lemma should be true. Why is it that the sum of the face sizes is 2e? There's a second lemma, part B. And the second lemma says, suppose that a planar graph has e edges, f faces, and the smallest cycle in a graph has length k. So little k, that represents the smallest cycle in the graph. We're talking about the smallest cycle, not necessarily a face, just the smallest cycle. A cycle doesn't necessarily have to be a face. All right, so k is the length of the smallest cycle. Then the claim is that 2e is greater than or equal to k times f. So take a look at the proof, fill in the blank here, and then give me a sentence or two at the end of that. And again, you can see by the amount of space I allowed, it won't require that much. But then this brings us to, now, the actual proof. So walk through steps C, D, and E. See if you can answer those questions, thinking about this relationship between faces and cycles, and before you know it, you'll come up with a proof that K33 is not planar. Well, once you've stepped through those things and thought about them a little bit, there are two more questions that you can answer. On separate paper, write up your proofs to the next two problems. 3, prove that K5, the complete graph on 5 vertices, is not planar. Also, try this number 4. Here's just kind of a random made-up graph, but you can also show that that thing is not planar. It's kind of cool that we can use this technique developed by Euler just to pick a graph at random, kind of analyze it carefully using edges, faces, and vertices, and figure out yes or no if this graph is planar or not. All right, give this worksheet a try, fill out what you can, and then during class, You can take some extra time and complete it. Ask me if you have questions, ask your fellow students if you have questions, and it will be due 2 hours after class. All right, good luck.